Welcome back. So today we're starting our last unit, our unit on modern physics. Now you might think that's a bit of a misnomer, modern physics, because basically we're going to be talking about things that have all been developed since the beginning of the 1900s, and most of them near the beginning of the 1900s. So how is that modern? Well, it's modern physics as opposed to classical physics. Classical physics, basically what was classical mechanics, basically, which was developed by Isaac Newton. Classical electricity and magnetism, which was developed by James Clerk Maxwell, both of which well before the early 1900s. Well, so modern physics, more modern essentially than classical mechanics, classical electricity and magnetism. Now, we are about to start lecture 20, which is entitled Special Relativity. Now, for the majority of this semester, the beginning of Physics 1112, we have been talking about electricity and magnetism, which can fundamentally be described using these four equations called Maxwell's equations. Last semester, or Physics 1111, we covered essentially mechanics, which is described using Newton's laws. Now, in the early 1900s, Albert Einstein was looking at these and he noticed that there was an inherent discrepancy between the two. Neither one of them, I should say both of them, could not be exactly right. There had to be something wrong with one of them, at least, to some extent. What we mean by wrong, we'll talk about in a little while. Now, if it were up to you, which one would you assume was correct and which one would you assume was incorrect? Would you assume that Maxwell's equations, very mathematical, dealing with electric fields, magnetic fields, would you assume that those were correct? Or Newton's laws, very concrete, dealing with things, for me, much easier to visualize, much easier to understand. Which one would you accept and which one would you say there must be some problem with them? Well, I would pick Newton's laws, and I would say, well, there's got to be something wrong with Maxwell's equation. But that's not what Einstein did. What Einstein said was, he thought Maxwell's equations were correct, and there must be some problem with Newton's laws. So, what did he do? What did he decide? Well, let's take a look. One very important idea that Albert Einstein had was that when something occurs, and where it occurs have to be put on a more equal footing, so to speak. In other words, if we describe when something occurs with a coordinate t, and where something occurs with the three, say, coordinates x, y, and z, these need to be put together into a four-dimensional point in what we will call space-time. So rather than having time and space separate, we're going to put them together and form a four-dimensional structure called space-time. And then a point in space-time, described by t, x, y, z, we'll call that an event. So when we're describing where something is and when it occurred, we'll call that an event. And an event is really just a point, a four-dimensional point in space-time. Now, to describe an event, to define these coordinates, we need a coordinate system. When we were solving problems in mechanics, we had freedom to choose whatever coordinate system we wanted. We could choose any old x and y coordinate system to solve our problem. Remember when we were looking at kinematics problems, we were throwing a ball or something like that, we could choose our coordinate system to be anywhere we wanted. It could be on the ground, it could be at the top of a cliff. We could choose our coordinates to have any orientation that we wanted. Left positive, right positive, up positive, down positive. If we had an incline problem, we could choose our coordinates to be inclined to match the incline of the problem. Well, the same is true for the coordinate system that we'll use for space-time. But we have even an additional freedom that we didn't use in this case in kinematics problems. We can actually choose a coordinate system that's moving. So imagine we have our coordinate system that's moving at some velocity. we have that freedom. We can now choose a coordinate system that's actually moving. So if we have two people, one moving relative to the other, they could each have their own coordinate system. Now, rather than a coordinate system, we'll actually use the term reference frame. So when we talk about someone's reference frame, we're just talking about their coordinate system. How would they set up their t, x, y, z coordinates to measure the coordinates of some event or something like that? So a reference frame is just another name for a coordinate system. Now, I'd like to do a little experiment, and I want to ask you a question. I'm going to create two events, and I want you to tell me how far apart are these two events. Okay? Now, here I have a 2-meter stick, 2 meters long, and I'm going to create two events. I'm going to snap my fingers 2 times. And I want you to tell me how far apart are those two events. What is the distance between the two events? Okay, ready? Now, here we go. Okay, let's try it one more time. Now, you might say the distance between those two events was 2 meters, because you would say one event took place over here, while the other event took place over here, 2 meters apart. However, I would say, in my reference frame, the distance between them is 0. Why? Because they both occurred at the same place. For me, one occurs right here, and the other occurs right here, at the same place in my coordinate system. So for you, the distance between those two events is 2 meters, but in other words, in your frame of reference. However, in my frame of reference, the distance between those two events is 0. Well, this is a very important point. Distance between events depends on your coordinate system. It's not a universal quantity. We've always thought that the distance between two things, say the length of an object, was always the same. It didn't matter who was measuring it. The length of a 2-meter stick is 2 meters. Doesn't matter who measures it, it's still 2 meters. Well, in this case, when we have two events that have different values for t, x, y, z, depending on who measures them, you'll get a different distance between them, a different physical distance. Well, this is an important point. We'll come back to this. So, I say the distance between these two events is 0. You say the distance between these two events is 2 meters. Who's right? Well, we're both right. We're measuring the same thing, well, the distance between these two events, we're measuring that thing using two different coordinate systems. And we get two different values because we're not measuring it in the same coordinate system, the same reference frame. Well, would it be possible, do you think, for someone to measure the time between two events as 0, while someone else measures the time between two events as something that is not 0, as 2 seconds or something like that? Would that be possible? Well, let's see. Maybe it is, maybe not. We'll see later on. Now, Einstein based his theory of special relativity on 2 postulates. A postulate meaning like an assumption. These are not things that will be proven, but they're assumptions that are made. So what are those postulates? Okay, the postulates of special relativity. The first postulate, sometimes referred to as the relativity postulate, states, all the laws of physics are the same in every inertial reference frame. Now, first of all, what do we mean by an inertial reference frame? Well, we know a reference frame means a coordinate system. So basically, an inertial coordinate system. Now, what do we mean by inertial? Well, for us, for now, inertial just basically means non-accelerating. A non-accelerating reference frame, or a non-accelerating coordinate system. In other words, a coordinate system moving at a constant velocity. Remember, I said that we were free to choose any coordinate system we wanted, even a moving one. Well, the moving one has to be moving at a constant velocity. It can't be accelerating. And I'll come back to that in just a second. So all the laws of physics are the same in every inertial reference frame. What that means is that there is no experiment that you could do in an inertial reference frame that would distinguish it from another inertial reference frame. Nothing that would distinguish the two. In other words, nothing to tell you what that velocity was, other than looking out of your frame and just looking to see if you're moving relative to another frame. There's nothing you could do to determine what your velocity is just being inside your reference frame. Let me give you a little example of this that you might have noticed before. Have you ever been in a situation where maybe you were in a car or a bus or a train or something like that, and you noticed that a car or bus or a train next to you started to move, and you weren't sure if you were actually the one doing the moving or if they were the one doing the moving the other direction? So maybe you're sitting still and you can't tell, are you moving this way or are they moving that way? Well, that's the basic idea, that there's nothing that you can do in an inertial reference frame to distinguish between, are you moving this way or are they moving that way? Well, let's imagine that we've got, say, 2 rocket ships with 2 astronauts in them. This astronaut does an experiment in their rocket, and this astronaut does an experiment in their rocket. There is nothing that either one of them could do to determine whether they are moving relative to the other rocket or not. Perhaps this rocket is moving this way at some velocity v, and this one is stationary. There's nothing this person can do to determine whether they are stationary and that one's moving, or are they moving this way while this rocket is stationary. Now, actually, I kind of cheated a little bit saying that one of them is stationary. The fact is that saying that they're stationary really doesn't mean anything. This rocket is stationary relative to that person. That person is stationary relative to their own rocket. But other things in the universe are always moving relative to them. There's no way to say that any particular rocket is stationary relative to any fixed reference frame in the universe. All you can do is say, well, one rocket is moving relative to this one, or you could say this one is moving that way relative to this one. There's no way to say that any particular rocket is stationary. We might think right now, well, we're on the Earth, we're stationary. Anything that is stationary relative to us also has to be stationary. But we know that the Earth is rotating. It's also revolving around the sun. The sun is moving through the rest of the Milky Way galaxy. The Milky Way is moving relative to other galaxies. So really, what is stationary? We certainly aren't stationary relative to the sun. We're going around the sun. The sun is not stationary relative to the rest of the Milky Way, etc., etc. There's no way to define anything as being absolutely stationary relative to the rest of the universe. All you can say is, say something is stationary relative to me. That paper is stationary relative to me right now. Okay, so there's nothing either one of them can do to determine any overall velocity relative to anything else. Okay? So that's the basic idea of the first postulate. Now, there's nothing in that that Isaac Newton would have disagreed with. There's nothing in that postulate that contradicts Newton's laws. What is the second postulate? The second postulate of special relativity, sometimes referred to as the speed of light postulate, states the speed of light in a vacuum is always measured to be c, which equals 3.00 times 10 to the 8th meters per second. Now, this is not exactly right, but to 3 significant figures, that's good. It's more like 2.998, something like that, to 4 significant figures. But to 3 sig figs, 3.00 times 10 to the 8th meters per second. Now, for my class, Physics 1112, this is going to be a number that we're going to be using a lot, and as I've mentioned before, it's a number that you need to remember. So on an exam or something like that, I won't be giving this to you. You need to remember that c, the speed of light in a vacuum, is 3.00 times 10 to the 8th meters per second. Now, why is this different than the first one? I mean, I said that the first one would not contradict Newton's laws. Does this contradict Newton's laws? Well, let's think about this. Let's imagine we're going to do an experiment way out in space. Now, we're doing it out in space so we don't have to worry about the gravity accelerating things or anything like that. So we're going to be way out in space, away from any gravitational fields. Let's imagine we have two people. So we've got person A here. Person A, let's say, throws a ball at person B. Now, person A throws the ball at 3 meters per second. Person B then catches the ball, and the ball is moving at 3 meters per second to person B. The ball is thrown at 3 meters per second. The ball is caught at 3 meters per second. Very simple. Now, what if person A is actually running toward person B to begin with? Well, let's see. So now let's say that person A throws the ball to person B, but person A is running toward person B at 2 meters per second. So while they're running, they throw the ball. How fast is the ball going to approach person B? Well, person A is running at 2 meters per second, throws the ball at 3 meters per second from their perspective. The ball will approach person B at 2 plus 3, 5 meters per second. Okay? Think of it that the ball is already moving at 2 meters per second because person A is carrying it. They throw it an additional 3 meters per second. From them, it's got to approach person B at 5 meters per second. Okay, great. That makes sense. Completely what Isaac Newton would have predicted. But the second postulate deals with light. Let's think about that. Now, let's imagine person A shines a light, a flashlight, at person B. The light leaves the flashlight at the speed of light, 3 times 10 to the 8th. Meters per second. The light then approaches person B at 3 times 10 to the 8th meters per second. Okay, that's fine. But now, what if person A is moving? Again, similar to the previous problem. So now, let's imagine person A is running toward person B at 2 times 10 to the 8th meters per second. Okay, so person A cannot run at 2 times 10 to the 8th meters per second. But just as a hypothetical problem, what Einstein would have called the Gedanken experiment, a thought experiment. Let's imagine that person A can move very, very fast, 2 times 10 to the 8th meters per second, and then shines a light which leaves person A at 3 times 10 to the 8th meters per second. How fast does that light approach person B? Well, from the similar problem we had before with the ball, we might think 3 times 10 to the 8th plus 2 times 10 to the 8th is 5 times 10 to the 8th. But no, postulate B, the second postulate, the speed of light postulate, always states that the speed of light is measured to be c, 3 times 10 to the 8th meters per second. So person B has to receive the light at 3 times 10 to the 8th meters per second. That is, according to the second postulate. That is completely different than what Isaac Newton would have said. This seems to completely contradict common sense. That if this person is moving at a speed and that is moving at that speed relative to this person should receive that at the sum of those two, but person B does not. Person B still receives the light as approaching this person at 3 times 10 to the 8th meters per second. The second postulate really does seem to contradict common sense. So, what can we get from this?